Fortunate today to have Abe Stern from NVIDIA. He is a data scientist on the solutions architecture team. And as a customer-facing engineer, Abe helps scientists, researchers, and supercomputing centers harness the power of GPU-accelerated computing through workshops, trainings, and hackathons. So I'm really excited about this presentation. We had Abe present at our booth, the SCSC booth at SC this last November, and I thought it was fantastic. So he's coming back for a full 1 hour slot in our Ecss Symposium this month. As usual, please mute when you are not speaking. For ECSSers and others, we were always looking for future speakers. We have a lot of slots open for the rest of the year, so if you're interested, please get in touch with me. I spoke with Abe earlier, and he is happy to take questions along the way. But given the large number of participants, I would like to manage the questions. So you can either raise your hand, they see there's a raise hand button down there, or you can type your question into the chat box. So with that, I am going to turn things over to Abe. So Abe, take it away.
Thanks very much, Bob. So as Bob mentioned, I'm a data scientist on the solution architecture team at NVIDIA. My background is computational chemistry, so I very much came from a scientific computing background. And at NVIDIA, I tend to work with customers in a variety of capacities, but I tend to focus on sort of the intersection of high performance computing, particularly chemistry applications, and machine learning. And I think that that's very apropos for the stuff that I'm going to be talking to you about today. So today I'm going to be talking about RAPIDS.
Oh, Abe, let me just interrupt you for 1 second.
Sure.
Right now we're seeing your speaker view with the slide on the side and the speaker notes. And I don't, there we go. Perfect.
Okay. Does this look right?
That looks good now. Thank you.
Okay, we'll go with that. So I'm going to be talking to you about RAPIDS, which is a suite of machine learning tools. It's a suite of machine learning tools, both for operating on GPU-accelerated data frames. So that's like a pandas drop-in replacement, and also cuML. So RAPIDS is two things. It's GPU-accelerated data frames and a suite of machine learning libraries in cuML. And also CUDA for GPU-accelerated Python, so CUDA-Python. So this is offered through a package called Numba, and it exposes the CUDA API for GPU programming. So we're going to be introducing both of these. These are both Python libraries, and I think it very much fits with this sort of theme of the intersection of HPC and machine learning. So to kind of set the stage, HPC is really transforming now, right? New users are coming and using supercomputers, and they're coming from domains that maybe are sort of new to high performance computing. So places like machine learning, deep learning, and obviously the old hats, high performance computing and scientific visualization. But particularly at this intersection between machine learning and deep learning, there is this ecosystem of Python tools, and so it's becoming the case where a lot of people are starting to use high performance computing resources from a Python ecosystem. So indeed, GPU accelerated computing is very much a thing, and we are currently accelerating 41% of the new top 500 systems in the world, including the fastest Summit and second fastest Sierra computers on the top 500. Really, I want to emphasize that the intersection of HPC and AI, these are not like standalone domains, right? AI is what's perhaps most exciting is that AI is complementing or augmenting traditional high-performance computing applications. So there are many cases where this is true. I've got a few of these highlighted here, but let me talk about just one, dig into one a little bit that's near and dear to my heart, coming from chemistry. So from a computational chemist perspective, if we're given a chemical structure, we know how to do the calculations to compute many different types of properties, right? But in a lead optimization search or a drug discovery type search, the problem is really inverted. We have a set of properties that we would like, or a range of properties that we would like. And the question is, how do we get to a structure? Unfortunately, chemical space is so vast that it's computationally intractable to simply search the problem, search chemical space. So using variational autoencoders, Dow Chemical has essentially inverted the problem to go from property to generate molecules of interest. So we really see this intersection of AI, where AI is complementing or augmenting high-performance computing. So another case, the Anakin force field. So those of you familiar with molecular dynamics simulations know that the computation of the forces is the most expensive piece of the calculation, right? So when we're interested in the dynamics of a chemical system, what we have to do is solve for these forces over and over and over and over again. This is very computationally expensive, especially if we're talking about an electronic structure type of calculation, which we would need to accurately describe, bonds breaking or the electron clouds reforming for complicated type of interactions. So the Anakin force field is a machine-learned potential that replaces the expensive electronic structure calculations that are typically used. So this is an exciting case where machine learning is, again, being used to augment or complement traditional high-performance computing in a way that, in this case, is unlocking the next generation of systems, both in terms of size and speed, right? Because with the machine-learned potential, the inference time for computing the electronic structure calculations is vastly reduced. So you can do much bigger systems, many more atoms for longer time scales. So it's worth taking a step back and asking, how is it that we got here with GPU accelerated computing? And the fact is Moore's law is ending, and GPU accelerated computing, which is a different approach to accelerated computing, is picking up where Moore's law left off. And we're not doing that just through delivering great hardware, but it's important to realize that there's a large software stack sitting on top of that. So we pick up where Moore's law left off, not just through hardware, but also a rich ecosystem of tools and libraries and APIs. And part of that is what I'm going to be talking to you about today. So it all starts with CUDA. That's our primary programming interface for the GPUs. And on top of that, we have a whole suite of tools, developer kits, frameworks, and finally, end user applications. So some of these I'll be talking to you about today in depth. So on the just above CUDA, you see in the machine learning box, we have cuDF and cuML and cuGraph. That's really the RAPIDS suite of tools that we'll be getting into. In deep learning, built into all the frameworks, we have our primitives in cuDNN and TensorRT, and also Cutlass. But we also have a suite of drop-in libraries, and these take the form of cuFFT and some others that I'll show you in just a moment. On top of that, we have all the frameworks. All the frameworks are built on top of cuDNN, Cutlass, TensorRT, and to some extent the CUDA primitives themselves. We also have the scientific applications that I'm sure everybody's familiar with, AMBER, NAMD, GAMES, VASP, Gaussian, and many others. So digging in a little bit into some of the relevant libraries for scientific computing. So in particular, I want to draw your attention to in the lower left-hand box, the linear algebra libraries. So we have cuBLAS, which is complete support for all the BLAS libraries, cuSparse, which is an optimized matrix, sparse matrix set of routines, CUDA-Math, which contains many frequently used math functions, Solver, which has various matrix decompositions, Cholesky decomposition, different matrix factorization routines, and cuRAND, which are number generators. So in total, we have over 500 GPU accelerated applications. Chances are, if you're using a major software package, well, you should definitely check out the GPU accelerated apps catalog. Over 600 applications GPU accelerated. So check out the GPU accelerated apps catalog. So one thing I'm not going to be talking to you about today, but definitely should be on your radar, is a programming paradigm, well, a compiler directive programming paradigm called OpenACC. So this sort of sits, you can think of this as sort of sitting somewhere between CUDA, programming directly in CUDA, and using a drop-in library. Okay, so it's a compiler directives based, so you use pound pragma or pragma hints, compiler hints to do your programming and express your parallelism. And the benefits are that you have one code base. If the compiler doesn't understand the compiler directives, they're safely ignored. So version control becomes very easy, and generally it's a really good on-ramp to GPU programming. You can express parallelism in relatively few lines of code, have the compiler do the heavy lifting of trying to parallelize the pieces of your code, and often to results that are as good, or in the case, or sometimes even better than perhaps not perfectly optimized CUDA implementations. So certainly if you're in C, C++, or Fortran, check out OpenACC. And in fact, Gaussian uses OpenACC, and VASP uses OpenACC. Okay, so let's dig into the main content, and we're going to start with Numba. So this is a way of programming, GPU programming directly in Python. So we are programming in CUDA directly in Python. So in particular, we have these CUDA provided variables, that I'll get into in a moment. It's relatively simple. We decorate our kernel functions with a decorator that's going to be JIT compiled to computer or to CUDA, or just-in-time compiled to CUDA, and we'll discuss what these CUDA provided variables are, how we launch a kernel, how we send data back and forth to the GPU, and just give you a basic introduction to CUDA programming. So we can write this very simple kernel, and then we'll kind of tear it apart and see how it works. And hopefully you'll take enough away that you could get started on your own. Okay, so GPUs do work in parallel, and I'm highlighting in green. This is some kernel perform work, and I've got it highlighted in green. We're going to parallelize that work. So work is done in individual threads. Okay, so I have this illustration. I have the block in blue, and the threads are in white, and I'm highlighting one particular thread in green there. Okay, so threads do the work. And we're gonna execute many of these threads in parallel. Okay, so some terminology. A collection of threads is a block. So I'm highlighting the block there. That's one block. And we have many blocks. Okay, and in fact, we can set the number of blocks that we want to execute a kernel. This is called the launch configuration. So a collection of blocks is associated with the kernel launch, and the configuration of blocks that we choose, so I'm just showing you two blocks, that we refer to as the grid. Okay, so the functions themselves we call kernels. So this is the GPU. This function is going to execute on the GPU, and highlighted in green here is perform work. So that's the kernel. And you see, now this is the C syntax. Those triple angle brackets are what the CUDA API, the CUDA programming interface brings, extends C, and by adding this syntactic sugar. Okay, so these triple angle brackets, that's CUDA C, and that's called the execution configuration or the launch configuration. Okay, in Python, that syntax is a little bit different. It's just square brackets, but nonetheless, everything else is the same. Okay, so the triple angle brackets 2, 4 specifies our execution configuration or our launch configuration. So in this case, the 2 represents the number of blocks that we're going to have in the grid. And the 4 represents the number of threads in each block that are going to execute. Okay, and every block in the grid is going to have the same number of threads. Okay, so we said the work is going to happen inside the threads, so somehow we need a way of mapping the threads to the work. Okay, and that's where the CUDA provided variables come in. Okay, so first CUDA provided variable that we have is grid dim. Okay, in particular, grid dim x, grid dim.x. Okay, so this is the number of blocks in the grid, and in this case, I've specified my launch configuration is 2 blocks, so my grid dim x is going to be 2. Similarly, I have a block index. Okay, now this block tells me which block, when my thread wakes up, when my kernel is being executed on the GPU and that parallel thread wakes up, block index.x will tell me what block I am executing in. Okay, so you can see I have the left-hand block highlighted in green. So when that kernel wakes up, block index.x if I'm one of those threads in the block 0, I'm going to wake up with a CUDA provided variable called blockindex.x, and it will be set to 0. Okay. And of course, similarly, if I wake up as one of those 4 threads on the right, my blockindex.x will be set to 1. Okay. Block dim.x again refers to the number of threads in the block. Okay, this is the launch configuration. I set it to 4. So I'm going to wake up and have block dim.x as 4. And that's going to be true in both blocks. And finally, thread index tells me which thread I am within a block. Okay, so highlighted in green is thread 0 and thread 1 and thread 2 and thread 3. And again, it refers to the index of the thread within the block. So in block 1, I reset, I'm again thread 0, but my block index in this case will be 1. Thread index.x is 0, 1, 2, and 3. Okay, so the whole game is that we're going to map our work to our threads to some data or vice versa. And so we do this through a combination of using the block index and the thread index. And so typically we use this formula. It's very common. You'll see it. Thread index plus block index times block dim. And we'll just briefly go through. So on the upper panel, I have this data array. We can think of this as an array. And so I have an array with index 0 through 7. And I want to map my 8 threads to unique elements of the array. Okay, so using this formula, thread index.x plus block index times block dim, we see that thread index of 0, block index 0 maps to the 0th element. If I move to the next thread, block index stays 0. And so incrementing just the thread index moves us to the data index of 1. And similarly for 2 and for 3. And then when we jump over to the next block, our thread index resets to 0, but our block index is 1. Our block dim is 4. And so we stride 4 elements across. And so thread index of 0 and block index of 1 maps to data index of 4. And hopefully this is pretty apparent how this works. Okay, so this is a common paradigm for mapping thread index and block index. We're mapping a launch configuration to, say, a linear array of work. Okay, so I do want to mention that it's possible to have 2 or 3-dimensional thread blocks and also grids. So in this case, I'm showing you, if you look at that launch configuration, in this case, I have specified a tuple 4, 4. And so I'm kind of mixing C and Python syntax there. So ignore the syntax, but this is a mixture of valid C and Python. But in any case, you see that I'm still specifying 2 blocks. Okay, so that's it's just a linear grid of blocks. But this time I'm specifying a 2-dimensional thread block. So I have a 4 by 4 matrix of threads. Okay, so this means that I'll have thread index.x and also thread index.y. Okay, so each of my blocks will have 16 threads and I'll know which thread I am by looking at threadindex.x, threadindex.y, and also blockindex.x. Okay, so let's look at the kernel that we specified earlier. So starting from the top, we use a Python decorator to specify that this will be just-in-time compiled to CUDA. And then I'm going to take my distance map function is going to take 3 parameters. Chords is an array. It's a 3-dimensional NumPy array that's indexed first by molecule, then by atom, then by Cartesian coordinate X, Y, or Z. Okay, so I have 3 indices to chords, and then I have a constant and atoms, and the final parameter edge feats is the result matrix. Okay, so I need to pass in a pointer to my edge feats, my return matrix. So now, in the next few lines, I use my CUDA provided variables, and I'm just renaming them for convenience. I have my thread index x, which I'm going to call tx, thread index.y, which is called ty, and bx, which is my block index. Okay. Now, in this case, I'm constructing a distance matrix. So I'm going to consider all pairs of atoms. So recall that my chords matrix is indexed by molecule, first of all, and atom is my second index. Okay. So what I'm going to do is map the distance calculation. Okay, I'm going to compute the distance between pairs of atoms. And so I'm going to take advantage of the fact that I have this 2-dimensional grid set up by indices thread x, tx, and thread y. And looking down at the calculation where I say map our thread indices to some work, notice that all I'm doing is computing the difference between chords tx and chords ty. And so I'm taking advantage of that 2-dimensional grid of threads to do my work. And I populate the edge feats, which is my return matrix with the result. So simple. So I have CUDA. I've expressed a problem in CUDA-Python. This is more or less, well, I wouldn't say native Python, but I'm certainly writing this within Python, and I just decorate the function. I take advantage of my CUDA-provided variables, and we'll talk about how to launch that kernel here on the next slide. Okay, so first of all, I mentioned we have that edge feats. That was the results matrix. Okay, so on the first line there, you see create results array on the GPU. This is the results array, right? So, well, taking a step back, keep in mind that we have 2 locations. We have memory on the CPU, and we also have memory on the GPU. And so we need to be aware of where our arrays and where our data exists, whether it's on the CPU or whether it's on the GPU, and we need to shuffle things back and forth. Okay, so my input data, I'll show you on the lines below, we move to the GPU. They exist in CPU memory, right? They're just normal NumPy arrays, and I'm going to move them to the GPU so I can read them, so the GPU kernel can read them and do some work. But the results array doesn't exist yet. So what I'm going to do in that first line is create the device array on the GPU. There's no need to create an empty array on the CPU and then send an empty array to the GPU. So what I'm going to do is create, I say CUDA.deviceArray. I'm going to create the array on the device. So that's much faster than transferring something over. We just allocate some space. I'm going to give it the shape. That's last XYZ plus 1, comma Atom max, and the data type. Okay, so now I have this allocated space on the GPU, and I have a pointer to that array, that edge feats GPU. So as I said in the next couple of lines, I have input data that already exists on the CPU. That's the structures coordinate mat. So these are just regular NumPy arrays. So I want to move those to the device and maintain pointers to the device, to those GPU structures. Okay, so the structures.GPU_GPU can only be operated on by the kernel. Same with the NAtom's GPU. Okay, so now we're going to launch the kernel. So this syntax might look a little funny at first, but in the square brackets, so recall that distance mat is the kernel that I just defined. That's the kernel function that we were just going through on the last slide. And in the square brackets, I specify my launch configuration. Okay, so the first parameter there, last XYZ plus 1, is the number of blocks. That is the number of molecules that I have. And the second parameter is the tuple 29 by 29. And that specifies the thread configuration, or the thread block configuration, and specifies that in each block, I want 29 by 29 threads. Okay, so a two-dimensional thread block. And then I pass as parameters to my kernel, as we went through, the input data, structures GPU, and atoms GPU, and edge feats GPU, which is the space that I just allocated on the device for the return array. Okay, so after we launch the kernel, the next thing we do is now we have the results array populated, but it's still on the GPU. And so I specify that I want to copy that back to the host, and I'm being very explicit about my variable naming here. So I say edge feats underscore GPU, copy to host, and I capture the edge feats CPU. So now that data is back on the host, and we synchronize to make sure that we're done. And that's it. So in just a very short handful of lines, we've written a kernel in CUDA-Python, launched it, and copied the data back. And I'll point out that this implementation is literally hundreds of thousands of times faster than a naive NumPy implementation. You can do better than that, obviously, if you go down to the C and have a very optimized implementation in C. But we did this in just a handful of lines in CUDA-Python, which, by the way, will still be many multiples faster than even the most optimized algorithm written in C or combination of C and assembly. So hopefully that's whet your appetite. So I will point out another option for GPU acceleration in Numba is the NumPy ufuncs, or universal functions. So here I'm showing you just quickly how this works, but this is automatic kind of vectorized approach. So we use a decorator to specify our data types, and we specify that the target is going to be CUDA. And we write our function to operate assuming that these are just scalars, okay? But the vectorized operation generalizes the operation to work on NumPy vectors, okay? So the vectorization is automatic, and it works for it doesn't completely cover every case of NumPy operations, but a good majority. So this is another option for GPU accelerated programming with Numba. Okay, so hopefully that's whet your appetite for GPU accelerated programming in CUDA-Python. I hope that we've provided a good overview of the CUDA concepts. And now we're going to shift gears and talk about RAPIDS. So RAPIDS is, as I said, a suite of tools for really data science in general. So there are tools for working with data frames, CUDF. Okay, this is meant to be a pandas-like drop-in replacement. QML, which is like a scikit-learn drop-in replacement, and cuGraph with operations for graph analytics that we're really not going to cover today. Okay, so hopefully you're at least familiar with some of the conveniences of working with data frames in packages like pandas. It's tremendous for tabular data, ragged data, time series data. And more and more, this is a commonly used package in data science, machine learning, deep learning. Working with pandas data frames from within a Jupyter notebook is a dream. The formatting is great. And you can explore data sets, operate on data sets, visualize different elements, select elements of the data sets very quickly and easily. So very convenient. So CUDF is a GPU accelerated implementation of a lot of pandas functionality. So you can seamlessly go back and forth from pandas to GPU data frames and vice versa, and most of the operations are just identical. So we'll go through some of those. If you're already using pandas, you're going to recognize all the concepts, and this is going to be extremely familiar to you. So let's get started. So first of all, ingesting a data frame. So reading a CSV. So GD is the CUDF or GPU accelerated data frame. So I've imported CUDF as GD. Okay, so when you see GD, that's CUDF. CUDF reads CSV. This is GPU accelerated ingest of a CSV file. This is dramatically faster in most cases. There's a substantial amount of calculation that goes in, computation that goes into ingesting a CSV. So we can accelerate that on a GPU, and we do. So if you don't believe me, try it out for yourself. You will be pleasantly surprised. But we're just getting started. You can also convert a data frame that already exists in pandas. So pd.read_csv. I have my pandas data frame, and I can specify gd.from_pandas structs_df. So I'm taking a pandas data frame and just converting it to a GPU accelerated data frame seamlessly. Of course, I can. I have, exploring functions, head, look at the first few lines of the data frame, and it pretty prints in a Jupyter notebook. And I can slice. This is integer slicing for row selection. So I can specify that I want rows 14 through 17, not inclusive. So I'm going to get rows 14, 15, and 16. And you can see the result below. I can select by name. So there are two ways to do this. I can either specify the name directly, gdf.atom in this case, or use the name as a string inside the square brackets. I can combine the two. So I can slice by row and column. So in this case, I want rows 14 through 21 and columns X, Y, and Z. Okay, let's get to some interesting stuff. So here, I'm going to compute a new column that we call norm. So like the L2 norm of a vector. So all I'm going to do is I'm going to say that my new column, I'm going to give it a name norm. So GDF in square brackets, the string norm equals x squared plus column y squared plus z squared. Simple as that. So now I'm doing operations on columns of the data. So I have the new column norm, you can see in the right-handmost column, computed from the sum of the squares of the elements of the x component, y component, z component.
Hey, Abe, do you mind if we have a question that came in? This is from Mona. She's asking, can CUDA read MATLAB data files directly?
I don't know about that. I have not heard that it can. That doesn't mean it can't, but I have not heard that it can. So I think the answer is no at this point, but I'm being a little bit tentative because, you know, we have, this is under constant and active development, and you should certainly go to rapids.ai to look for the complete list of input formats that it supports.
Great, thank you. And then Mona, did you have anything else to follow up with on that question?
No, that's it for now. Thank you.
Great, thank you. All right, go ahead, Abe.
Thanks. Okay. So we can construct a Boolean series. So simply by taking, we're going to take the norm that I just computed, and we're going to construct a Boolean series from norm values that are greater than 3. So gdf.norm greater than 3 returns a series where each element has the Boolean value of whether that was true or false. Okay, so we could either store that logical series as its own variable, own series, or we could use it directly to slice and select data. So in this case, I'm showing you that, you know, let's say we want columns, the molecule name and atom, where the GDF norm was greater than 3. So you can see in the second line of syntax how we would approach that. We can look at unique elements. So this is looking at the whole data frame. Give me the list of unique atoms. So dot unique. Okay, and finally, perhaps the most useful thing about GPU accelerated data frames are when well, certainly accelerating any kind of operations between the data frames, the GPU acceleration is likely going to be worthwhile. But what's most interesting to me are the user-defined functions. So this lets us define any kind of operations that we want, user-defined functions between columns. So in this particular example is a little bit contrived. I'm just labeling the atom's mass. So I'm constructing a new function, a new column, and it's going to contain the mass of the atom. Hopefully that's clear. So the syntax is a little bit perhaps foreign, but this is how we do it. Okay, so we loop over the atom code. This is our incoming vector atom codes, and we're going to enumerate. We're going to loop and enumerate over that incoming data. This, of course, could be other elements of other columns in the row. We could have a list of columns, in which case we would enumerate over a zip. Hopefully that's clear. And then we're going to store the result using the enumerated index I. Okay, so if the atom code equals 0, then the mass is 12.011, so that's a carbon, and so on. So this is how we define our user-defined function. And the way we're going to apply it is, again, we have to use a little bit of extra syntax here, but we're going to specify that the input columns to my user-defined function are the column, is the column atom codes. The outbound columns, we have to specify a dictionary here, and the elements of the dictionary are going to be the name of the column coming out, so that in this case it's mass, and we have to give it a data type. So we're going to say mass is going to be a float 32. And then finally, we do have to include keyword arguments. Okay. So that's really all there is to it. We specify that we want to apply rows, the user-defined function label mass. We let it know what input columns we're going to operate on, and this could be obviously more than one. We have to specify the output columns that are coming out. This also can be more than one, and we have to give the output columns a data type. So relatively easy to construct and apply user-defined functions.
Great. Abe, can I interrupt with another question that came in?
Yep.
This was from Chris Reedy. I installed Numba with pip3 install Numba, and he asked, what is the best way to run RAPIDS? I see there is a RAPIDS 0.0.1 and a RAPID Pi 2.6.0 and RAPID framework.
Well, first of all, hi, Chris. I know Chris, and well, so the official answer is look at the GitHub RAPIDS page for recommended practices for installing. I will share with you that my favorite way is to use the Conda installers, but we do support pip installs. There's a great, if you go to rapids.ai, there's a great, under getting started, there's a great automated tool for, selecting how you want to install, and then it gives you essentially like the command line for how you would install. I want to use pip with the CUDA toolkit 10.0 with Python 3. You select with, you make your selections on what your system configuration is. Like I just said, pip with, CUDA 10, Python 3, and then it gives you the recommended command line. And, in the case of Conda, it gives you the channels that you need to include to make sure that you get it properly installed. Hopefully that answers your question, Chris.
Okay, yep, I see replied yes. Chris, anything else that you wanted to follow up on there? Otherwise, we will move on. Great, thank you. All right, go ahead, Abe.
great. Okay, so we had just applied our user-defined function, and I guess I'm just showing you the result here. So we have our new column mass, and you can see carbon atoms have a mass of 12, hydrogen's mass of 1, and nitrogen's mass of 14. So it worked. Okay, and there are there's a lot of other functionality that's supported, a lot of other kind of built-in operations for columns. A couple of these are shown here. This is taken directly from the documentation: element-wise max, element-wise min, absolute value, clipping, and we went through how to define user-defined functions and kernels with apply rows. Okay, so here I'm just showing you some interesting string operations between columns. So I've ingested a CSV file with read CSV. On the next code, I'm doing a series of string operations. So train GDF dot molecule name. So I've selected molecule name column. Dot str is doing a string conversion. Dot split is now splitting on the underscore, and I'm taking the first element of that. So I'm actually taking the second, it's the numerical part. We have a string underscore, right? It's the second element, 0 indexed, and as type integer. So I'm extracting the integer value of the molecule name there. The next line of code hashes that molecule name, and finally splitting up into a test train set by constructing a mask mod 4 of that hash. Okay, so very quickly, in just a handful of lines of code, we can do things. If you grew up like I did programming in C, you can imagine how many lines of C code this would take. So we reap all the benefits of having a high-level functionality in Python with GPU-accelerated data frames. So even on massive data sets, this stuff is extremely fast. Okay, so very briefly, just wrapping up, I want to cover a few of the algorithms that are in 2ML, which is sort of the other, I almost think of it as other half of RAPIDS. But realistically, RAPIDS is a suite of tools. cuML is one component of that. But cuML has all the machine learning algorithms that you're familiar with. So for example, k-nearest neighbors, dbScan, which is density-based clustering, k-means clustering, singular value decomposition. Again, these are all GPU-accelerated scikit-learn replacements. So if you use these algorithms in scikit-learn, it's more or less the same method calls. You'll be familiar with how to use the methods, it's meant to be a scikit-learn drop-in replacement. Principal component analysis, and finally XGBoost. But this was not an exhaustive list. These were just some of my favorites. So as of, we're constantly adding new algorithms to this. So as of version 0.13.0a, this is the complete list. So among those I didn't mention, we have TSNE, T distributed stochastic neighbor embedding, UMAP, ordinary least squares regression, a couple of variants of linear regression, elastic net regression, random forest classification and regression, support vector machine classifiers. For time series operations, we have linear Kalman filters, Holt-Winters exponential smoothing, and ARIMA autoregressive integrated moving averages. And more coming. This list is constantly updated. The RAPIDS team is constantly working to add new algorithms. So if you use an algorithm that you would like to see GPU accelerated, also do let me know. We take that feedback very seriously, and maybe it'll be in the next release. So finally, just wrapping up, I do want to promote our container repository. We have over 50 GPU optimized software containers, containers ranging from deep learning and machine learning to high performance computing, genomics, and scientific visualization. So it's free to use. ngc.nvidia.com is our container repository. Containers are freely available to download and use, so check it out. With that, I'll conclude. Thanks very much.
Great, thank you, Abe. We have another question that's queued up. This is from Sean Dowdy, who asks, how are large data sets managed between CPU and GPU over PCI bus? Is it just magically optimized?
So there are a couple of answers to that. Ultimately, you do have to get the data from the GPU, from the CPU to the GPU, and probably get the result back. So usually that is through the PCI bus. Although in the case of power systems, for example, you have optimized interconnect between CPU memory and GPU memory. But if you're talking about so one answer to that is you try to amortize the cost of moving that data back and forth by expensive operations. So if your operations are relatively computationally intense, then that cost is going to be amortized relatively easily. Hopefully that makes sense, right? If you have 2 million or billion or whatever rows, and you need to do an operation serially on the CPU, going row by row by row by row, then you can imagine if we could do all of those operations on all those rows simultaneously in parallel, then even accounting for the time that it took to move the data frame to the GPU and back would still be less than the time that it would take to do all those operations in sequence, right? The other answer to that question may be, and I'm not sure if this was part of the question or not, but for really large data frames that won't fit into GPU memory, Dask, all of this is built on Dask. And so Dask gives you the ability to split share the work between multiple GPUs and even multiple nodes. So truly, the sky's the limit in terms of the size of data frames that you can operate on.
Great, thank you so much, Abe. Do we have any more questions? Let's see, we're just past the top of the hour, but I think we have time for a question or two. Oh, and I see a follow-up from Mona. So Mona, do you just want to go ahead and ask?
Okay, sure. Thank you. Yeah, I have a naive question about the CPU and GPU transfer. So I've never used this before, so this is naive. But can you just load the data directly into the GPU, do the operations, and then pull it out directly from there? Or does it have to go through the CPU?
Well, it depends on what level you're talking about, but I'll say sort of at a high level, that really is what functions like gd.read CSV do. So they attempt to read the data directly into GPU memory. And for all intents and purposes, it doesn't hit CPU memory. But if you're asking at a very low level, like you want to know where the bits are moving on the hardware and so on, it does actually travel through the CPU memory. Now, we have something called GPU Direct, which in some cases is designed for reading directly into GPU memory and never touching the CPU memory at all. But that's a different conversation. But another answer to your question is, so there are tools, going back to that higher level. gd.read_csv reads the data directly into GPU memory for all intents and purposes. And then you can do operations on that data while it's in the GPU memory. And you can keep doing operations. If you have a series of operations that need to be performed, for example, you can go seamlessly from cuDF to doing some operations in Numba, to doing some analysis in QML, all operating on that GPU data structure resident in GPU memory, and never have to transfer the result back until you're completely done and you want to, store it to disk or visualize it or something like that. So hopefully that makes sense.
Yes, thank you, Abe.
Do we have any more questions? If not, I have one question of my own. So of course you've been talking about working in Python. When it comes to data frames, though, I love that we have pandas, but I was, like many of us, first exposed to data frames in R. Is there any support for GPU accelerated data frames in R?
Not that I'm aware of, although at least not in conjunction with the RAPIDS effort. There may be some work on GPU accelerating R itself, but I'm not privy to those projects. So I would have to look into that
Okay,
more.
yeah, I mean, I personally much prefer Python, but I know that a lot of our researchers, say from the social sciences, political science, that they grow up as R programmers.
Mm-hmm. That is true, and we hear a lot of feedback on R. I'm just not up to speed on where we're at with R.
Okay, great, thank you. Do we have any more questions for our speaker? All right, if not, Abe, thank you so much. That was great. Thank you for taking your time to talk about Numba, RAPIDS, and GPU programming. I think this is all very useful.
Happy to do so. Thanks very much for the invitation.
Great, thank you, everybody, and hope to see you all next month for our next Ecss Symposium. Alrighty, bye-bye.